I'm Madhu, and today my partner Anish and I will be discussing our final project, reproducing, validating, and enhancing ClinicalBERT. We'll start by contextualizing the problem space and the original paper, discussing its approach and claim results. Then we'll dive into our contributions, which involved reproducing the paper, validating results, and making ablations. Clinical notes are often underutilized in the medical domain, yet with the help of deep learning models, they have the potential to reveal high-quality physician-assessed semantic relationships between medical concepts, which would otherwise involve a human perspective. The paper we reproduce sets out to solve how we might effectively model clinical language, which can be useful in domain-specific predictive tasks. The original paper presents ClinicalBERT, a modified BERT model, as a flexible framework for learning deep representations of clinical notes. It includes an added self-attention mechanism computed on an input sequence using associated clinical text embeddings, and it's pre-trained on unstructured clinical notes from the MIMIC3 dataset. ClinicalBERT leverages two unsupervised tasks, mass language modeling and next sentence prediction, followed by a problem-specific fine-tuning phase. The task here to predict 30-day readmission using clinical notes from discharge summaries and early notes. The provided results from the original paper compare the proposed and baseline models on three metrics for 30-day readmission prediction. Here we can see that ClinicalBERT outperforms all three baselines using both discharge summaries and early clinical notes. At the top, we see that ClinicalBERT has greater precision and recall with discharge summaries, whereas on the bottom, the AUROC and AUPRC results show that ClinicalBERT has more confidence and higher accuracy.
Hi, I'm Anish, and next we will discuss our contributions. Here is what the entire pipeline looks like. We created two models as the paper reported, one optimizing readmission prediction based on discharge summary notes, and one based on early notes, defined as notes written within the first 3 days of admission. The method leverages a pre-trained BERT pipeline with two phases, followed by a context-specific fine-tuning phase. The learning objective was a function of the sum of the log likelihoods of predicted mass tokens, and the log likelihood of the binary variable indicating whether or not two sentences are consecutive. The trained model had 110 million parameters. The first baseline model, Bag of Words, uses count vectorizer embeddings as input for a logistic regression model using L2 regularization. The second baseline model, BiLSTM, is a bidirectional sequence processing model with two LSTMs, taking in word-to-vec embeddings as input. The third baseline model, BERT, follows a multi-layer bidirectional transformer-encoded architecture, and it uses stacked self-ascension mechanisms and pointwise, fully connected layers for both the encoder and decoder to learn deep bidirectional representations from unlabeled text by jointly conditioning on both the left and right context in all layers. Comparing the results with the original paper, we found that ClinicalBERT has the highest AUROC, AUPRC, and RP80 scores across all contexts. Using discharge summaries, we reproduced and improved AUROC and AUPRC to within 3 to 4% of reported values for ClinicalBERT. Using early clinical notes, our reproduced ClinicalBERT model improved AUROC and AUPRC by 22% and 19% of the reported values in the original paper. Our reproduced baselines models did outperform their respective reported values, with the exception of BERT, but these results still support the author's claim that ClinicalBERT outperforms all baselines. So it is indeed effective for language modeling in the context of clinical notes. We tried a few things to try and boost the performance of ClinicalBERT. The author suggested we try to improve models by finding more high-quality clinical datasets, but such data is not highly available. We tried to do so through data augmentation, the practice of expanding datasets using existing data. One way to do this was to simply redefine early notes to allow notes within the first 5 and 7 days of admission, rather than just 3 days. The performance can be seen below. And another method we tried was to synthetically add new rows of data by randomly swapping words and trying synonym replacement. We updated ClinicalBERT models to migrate from the PyTorch pre-trained BERT library to use transformers, a library of over 32 state-of-the-art pre-trained models for NLP tests. By re-implementing the forward method, replacing two optimizer, and migrating libraries, we were able to decrease runtime by nearly 84%. The AUROC and AUPRC for both models were within a 1% margin of the previous models. These findings reinforce the author's speculation that fine-tuning may yield better performance. To the left are the claims made in the original paper. We validated Claim 1 by reproducing ClinicalBERT and comparing results. We validated Claim 2 by reproducing and comparing evaluation metrics of ClinicalBERT and all three baselines on a 30-day readmission task. Notice that the third claim is postulated in the discussion section of the original paper, but no experiments or results were presented. While data augmentation didn't improve much, we were successful in reducing compute time to 84% while maintaining all performance metrics. Thanks for listening, and we hope you learned something useful.